So let's get started. Now, uh, today we are starting a new chapter, which is Number Theory and Cryptography. And this is the chapter 7 in the book. And we'll be discussing section 7.2 in particular, which is divisibility and modular arithmetic. Now, we'll be going through some definitions and theorems and corollaries. We'll be also discussing some problems related to those. Now, if we will start with the definition of the division. If A and B are the integers with A not equal to 0, then A divides B if there exists an integer C such that B is equal to A times C. Now, what it means is that if we have A and B as integers such that A is not equal to 0, then A divides B if there exists an integer C such that B is equal to A times C. And A divides B is represented with this A bar B, where this means A divides B. Or in other words, it will look something like this: A divides B. And it's saying that if A is not equal to 0, then A divides B only if B is a multiple of A, or in other words, this is equal to A times C by A, and this will cancel out, and this gives us the number C. Now, as I told you, when you divide B by A, it will give us an integer C. That's one condition. And second is that if A does not divide B, then it's the case when B divided by A does not give us any multiple C. Now we can think of an example where A is equal to 3 and B is equal to 6. Now let's check whether A divides B. Let's check it. So in this case, B by A will be equal to 6 by 3. It gives us a number 2, which is an integer. So therefore, A divides B is true. Now, if we have another case where B is equal to 4 and A is 3, then B by A is equal to 4 by 3, and it does not give us any integer. It does not give us any integer. Therefore, A does not divide B. Now, there is another theorem related to division. where we have A, B, and C. Let's assume that A, B, and C are three integers where again A is not equal to 0. Then if A divides B and A divides C, then this implies A divides B plus C. Also, if A divides B and if A divides B, then A will divide B times C. Now, and the third condition here is if A divides B and B divides C, then A will divide C. So what this means is okay. Alex is asking, can you go back real quick? You mean the OneNote or the slides? Okay. This part? Are you talking about this slide? Okay. So we have three cases here. In the first case, if A divides B and A divides C, then this implies A will divide B plus C. Second case, if A divides B, then A will divide B times C. And in third case, if A divides B and B divides C, then A will divide C. Okay. Share application screen. So we have three cases. In the first case, so we are assuming we have three integers, A, B, and C. At the same time, A is not equal to 0. Then in the first case, what the theorem states is if A divides B and at the same time A divides C, then A will divide B plus C. So in other words, this is like if P is divisible by A and C is divisible by A, then B plus C is divisible by A. Now let's think of an example where A is 3 and B is 6 and C is 9. So B by A in that case will be 6 by 3 and this is divisible, so this will be 2, and at the same time C by A will be equal to 9 by 3. This will be 3 times 3. Then we'll check whether B plus C by A will be divisible or not. So B plus C will be equal to, B plus C by A will be equal to 9 plus 6 by 3. This is equal to 15 by 3. So this is 3 times 5. So this is also divisible. So this part is true. Now let's take the second case. Let's take the second case where the theorem states that if A divides B, then A will divide B, C, and C is an integer. Now, if we have A equal to 3, B equal to 6, and C as any number, let's say 4, since it's an integer, then B times C by A, which this both mean the same, will be equal to 6 times 4 by 3. So this will be 3, 2, and 8. So this again is true. Now let's have a look at the third case, which is if A divides B and B divides C, then A will divide C. So this means so Nicholas is asking, can you scroll up the number 2 just for a second? Yeah, sure. Okay. So if A divides B and B divides C, then A will divide C as well. So this means if B is divisible by A and C is divisible by B, then C is divisible by A as well. Now let's look at this case where A is 3, B is 6, and C is let's say 18. Then in that case, B by A is equal to 6 by 3, which is equal to 2, and C by B is equal to 18 by 6 is equal to 3. Then let's see whether C is divisible by A or not. Now so far we were fine with this. Now let's check whether C is divisible by A or not. So this will be equal to 18/3, and this again is true. 3 times 6. So this property of the theorem also, this part of the theorem also holds true. Any questions so far? Okay, let's move forward. Then we have another corollary, which states that the corollary states that if a, b, and c are integers where a is not equal to 0, such that a divides b and a divides c, then a will divide m times b plus n times c, where m and n are integers. So m and n are any two arbitrary values, but they have to be integers. So let's check whether this corollary is true or not, or just to make sense of what this means. Uh, let's take an example here. So the corollary states that if a, b, and c, they belong to integers, and at the same time a is not equal to 0, that's one part. Second thing that it states is that a divides b and a divides c, then this should mean m times a plus n times c is divisible by a, or in other words, a divides m times b plus n times c. So let's take an example where a is equal to 3 and b is equal to 6 and c is equal to 9. Someone has any question? Alex is asking, wait, is it MA or MB? Uh, yeah, it's MB here. I think it's MB. That's what the corollary states. It's MB. Sorry. Thanks for correcting me. So we're taking an example where A is equal to 3, B is equal to 6, C is equal to 9, and let's say M is equal to 1 and N is equal to 2. So if you look at this part, which is A divides B. So in this case, this is 6 by 3, and it's true because, so it's true, it is divisible. The second part, which is A by C, that is 9 by 3, and again it's true because we get 3. Now let's check whether A divides m times B plus n times C. So what we'll get here is 1 times B, which is 6, plus 2 times or n times C, which is 9. Is it divisible by 3 or not? So this will be equal to 6 plus 18 by 3. So we'll get an integer because 6 plus 18 is 24. 24 by 3. 3 times 8 gives us 24. So this proves that A divides m times B plus n times C. So is there any question so far? Okay. Now, the division algorithm, in a typical division algorithm, what we have is we have things like divisor, dividend, quotient, and remainder. And so if A is an integer and D is a positive integer as well, then there are unique integers Q and R with R ranging from 0 to D, such that A is equal to D times Q plus R. So in that case, D is the divisor. Let me show it on the OneNote. So it will look something like this. A is equal to D times Q plus R, and R will range from 0 to D, so it will be less than D, and will be a value between 0 and D, and this part is called as dividend. This is called as the quotient, and R is the remainder, and D is called as the divisor. Now, you might be already aware of this because if we take a particular example, like let's divide 27 by 5. So this will be 5 times 5, and this will give us 25, and we'll have 2 here. So this is called as the divisor, this part. This is the quotient. This is the dividend, and this is the remainder. Now, if you were to represent it like this, we'll have 27 is equal to 5 times 5 plus 2. Now, when we have to, so this division algorithm, it gives us two things. It has the division part and it has the modulus part. So if we want to get the value of the quotient will be Q is equal to A divides A divides A divides D, or in other words, uh, if we take this example, 27 by 5, or in other words, it's like A by D. And the remainder is obtained by A mod D. So if we were to use this part, this will give us the remainder in this case, which is 2. Now, let us move further. That was all about the division algorithm, and we'll be using this in some examples later. Now, there is another concept which is called as congruence, and the congruence symbol so the congruence symbol, or the congruence relation, in the congruence relation is represented with this is represented with this symbol, which is where you have 3 parallel lines, unlike the equal to symbol where we have 2 parallel lines. And we can say that A is congruent to B mod M if, so the definition states that we can say A is congruent to B mod M when M divides A minus B. So the notation A is congruent to B mod M says that A is congruent to B mod modulo M. We say that this entire thing is a congruence and that M is its modulus. Two integers are congruent to mod M if and only if they have the same remainder when divided by M. And if A is not congruent to B mod M, we say that we represent it with this symbol, which means that it's not congruent. Now, to simplify it, uh, let me explain what all of this means. So it's a relation, congruence is a relation, and it is represented with this symbol. And we can say that A is congruent to B mod M if B minus A is divisible by M. It gives us some number, let's say S. It gives us some integer, let's say S. So if this property doesn't hold true, then A is not congruent to B mod M. It's not congruent to B mod M. Let's take an example. Let's check whether 17 is congruent to 5 mod 6. We have to check whether this is congruent or not. Now the condition that I told you, that if it is of the form of A is congruent to B mod M, then A minus B should be divisible by M. So in this case, A is 17 and B is 5 and M is 6. Now let's check whether it's divisible by M or not. So 17 minus 5 is equal to 12, and 17 minus 5 by 6 is equal to 12 by 6. So it is divisible. We get 2. Therefore, 17 is congruent to 5 mod 6. Now let's check for another problem. Let's check it for another problem where we have 24. We have to check whether 24 is congruent to 14 mod 6. So in this case, B minus A will be equal to 24 minus 14, which is equal to 10. And M in this case is 6. M is 6. This is B minus A. And B minus A in this case cannot be divided by M. So M does not divide B minus A because we have 10 and 10 is not divisible by, it's not divisible by 6. So therefore, this is not congruent. Now, do you guys have any question related to this? Okay. Now the thing worth noting is that these are. So anyone has a question? Is it A minus B, or is it, Amanda is asking, is it A minus B or B minus A? It's B minus A. Okay. No, sorry, it's actually, thanks for correcting me. It's A minus B, because if you look at if you look at if you look at the relation, it's of the form of A is congruent to B mod M. So we are checking here 24 minus 14. So this clearly is A minus B. So thanks for correcting me. Let's move forward. Let me correct this. This is M does not divide A minus B. Now we have to know the difference between the congruence and the equal relation. Now, if you look at the congruence part, um, A is congruent to B mod M. Uh, it's a relation where we are checking this condition where A minus B is divisible by M or not. But if you look at this, which is A mod M is equal to B, this is a function. Now, this will be clear with this term where let's say A and B are integers and M is a positive integer. Then A is congruent to B mod M if and only if A mod M is equal to B mod M. So what it means is that if A and B are integers, they belong to integers, and M belongs to positive integers, then A is, so this is a theorem, then A is, so this theorem states if um, A and B both are integers and M is a positive integer, then A is congruent to B mod M if and only if A mod M is equal to B mod M. Now let's take the same example, the one that we discussed previously, where let's say we have this 17, A is 17, and we knew that it was congruent to 5 mod 6. So we did check it because 17 minus 5 was divisible by 6. And let's continue from there onwards. Let's see whether A mod M is equal to B mod M. So uh, if you take a look at the definition of the remainder, when we were discussing the division algorithm, so the remainder was equal to uh, if we have something like if we are dividing, let's say, uh, a number x by y, so this will give us a remainder r, and that was of the form of a mod b. So a mod b will give us the remainder. So in this case we have 17 mod 6. So 17 mod 6, if you divide 17 by 6, it will be equal to 17 by 6 will be equal to 6 to this will be 12, and we'll get 5. So this is 5, and let's check it for b mod m. So b in this case is 5. 5 mod 6 will be 5 again. Because 5 is less than 6, so we'll get, if we divide it, uh, we'll get 5 as the remainder. So both of these are the same values, therefore this this theorem holds true. So we were able to find that if A is congruent to B mod M, then this property is true if and only if A mod M is equal to B mod M. So is there any question so far? Should we move ahead? Okay. Now we have the congruence of sums and the congruence of products. So the congruence of sum theorem and product, it states that if m is a positive integer and a is congruent to b mod m and c is congruent to d mod m, then a plus c is congruent to b plus d mod m, and also ac is congruent to b times d mod m. Now let's prove this. Let's try to prove it and check whether this is true or not. So what the theorem states is that if m is a positive integer, and if so these things are given, if A is congruent to B mod M, and at the same time C is congruent to D mod M, then A plus C is congruent to B plus D mod M, and A times C is congruent to B times D mod M. So this is called as the congruence of sums and products. Now, if you recall at the very beginning, I told you A divides B if A divides B if B is equal to AC, or in other words, A uh, or in other words, B by C, B by A will give us some number, let's say T. Only then we can say that A divides B. So this was one thing, and the other thing uh, told you was if we have something of the form of A is congruent to B mod M, this is true only when A minus B is divisible by M. So it gives us, let's say, some number S. Now, if you rewrite this thing, if you rewrite this will be, so this is S, this is not 5. So if you rewrite this will be of the form of A minus B is equal to, now if we multiply M on both sides, this will be S times M, and A will be of the form of, if we add B on both sides, so this is multiplying M on both sides, and this is, if we are adding B on both sides, this will be B plus S times M. So the thing that's given to us is the two things that are given to us are A is congruent to B mod M, and the second thing is C is congruent to D mod M. And at the same time, we know that A, when A is congruent to B mod M, then in that case, A will be equal to B times SM, where S is some constant, some integer. So we can similarly hold the same assumptions about this statement where C is congruent to D mod M. So this will be equal to, let's say C is equal to D plus T times M. Now let's call this as 1 and let's call this as 2. Let's add, this is B plus S of M, S times M. So this will be equal to, if we adding 1 and 2 on, adding 1 and 2, what we'll get is A plus C will be equal to B plus S times M plus D plus T times M. Now we will take the terms that contain M together. We'll just sum them up together. So this can be rewritten as B plus D plus S times M plus T times M. So this will be equal to B plus D plus S plus T times M. Now S plus T, let's say that it's uh, since it's a constant, let's say that S plus T is equal to, let's call it X. So this will be B plus D plus X times M, because X is equal to S plus T. So if you look at this and consider this to be one entity, this to be one entity, then it's exactly of the form of this equation, which is, this is exactly of the form of this equation, which is A is equal to B plus S times M. So we can say, using this, we can say that A plus C is congruent to B plus D mod M. So is there any confusion so far here? Any questions? Okay, let's try to prove the congruence of the products. So what we'll do is we will multiply first and second. So we'll multiply first and second in this case. What we'll get is A times C is equal to b plus s of m times d plus tm. So this will be equal to b times d if we multiply with b, then plus b times t times m plus s times m times d plus s times t times m square. Now we will take all the terms that contain m separately. So this will be equal to b times d plus b times t plus s times d plus s times t times m times m. Now we can think of this entire thing as a constant, which is an integer. Let's call this as y. So this will be equal to b times d plus y times m. Now if you look at this and consider this to be as one entity, this to be one entity, it exactly looks like the equation 1, which is a is equal to b plus s times m. So this proves that a times c is congruent to b times d mod m. So this proves the congruence of products. So any questions so far? Okay, let's move forward. Now, let's take an example where we'll see the congruence of sum and product for 7 is congruent to 2 mod 5 and 11 is congruent to 1 mod 5. So we are given uh, two congruences where 7 is congruent to 2 mod 5, and the second is 11 is congruent to 1 mod 5. Now we have to check the congruence of sums and products. Let's take the first case, which is a plus c is congruent to b plus d mod m. So this will become 7 plus 11, and we have to check whether this is congruent to 2 plus 1 mod 5. So if you look at this, this will be 18 is congruent to 3 mod 5, and the property was that a minus b should be divisible by m. In this case, we have to check whether 18 minus 3 is divisible by 5 or not. So this will be 15 by 5, and 5 divides 15, which is 3. So therefore, the congruence of sum property is true. Now, let's try to check it for the congruence of products. The congruence of product states that A times C is equal to B times D mod M. Now, in this case, we'll have 7 times 11. Let's check whether it's congruent to 2 times 1 mod 5. So if you look at this, this will be 77, and this will be 2 mod 5. So 77 minus 2 is equal to 75, and 75 is divisible by 5. It is divisible by 5 because 75 is the multiple of 5. Therefore, the product property, the congruence of products also holds true here. So any questions so far? Now let's have a look at some of the algebraic manipulation of congruences. So what it states is that if we multiply both sides of a valid congruence, so the condition is that it has a congruence by an integer, then it will still preserve its validity. So if we have a congruence, A is congruent to B mod M, and if we multiply it with an integer C on both sides, then C times A will be congruent to C times B mod M. So that's the that's one property. That is, if we multiply by an integer on both sides, then it will still be valid. The congruence will still be valid. So the other property is if we are adding an integer on both sides of a valid congruence, then it still preserves the validity. Now, if we are adding a constant C on both sides, an integer C on both sides, this will be C plus A is congruent to C plus B mod M. So this will still be preserved. The congruence will still be preserved. Now, if we are dividing by a value on both sides, then it's not necessary that the congruence will be maintained. Now, if you look at this example, where 14 is congruent to 8 mod 6, so in this case, this is a valid congruence. Now, if we are dividing both sides by 2, if we are dividing both sides by 2, what it will give us is the values 7, and it will be of the form of 7, and we have to check whether it's congruent or not. 4 mod 6. So in this case, a minus b will be equal to 3, and 3 is not divisible by 6. So division does not necessarily preserve the validity. Now, is there any question here so far? Okay. Now we have another corollary, which states that if m is a positive integer and a and b are also integers, then if we have a plus b mod m, then it is equal to a mod m plus b mod m, and this whole times mod m. So this is another part of this corollary, which is a times b mod m is equal to a mod m times b mod m, and this entire thing is having mod m. So this we consider this to be as an entity, and this will be mod m. Now uh, this is another concept which is called as arithmetic modulo m, and uh, if we have z of m, and it's a set of non-negative integers such that m ranges from 0 to m minus 1, and this operator plus m is defined as m plus a plus m, or b is the same as a plus b mod m. So whenever you come across a statement like this or an expression like this, this is the same as a plus b mod m. Similarly, if you come across an expression like this means with dot m. So this means it's the same as a times b mod m. Now, if we have an example, let me share it here. So we have a set of non-negative integers, which is represented by z of m, and here m such that m ranges from 0, 1 all the way till m minus 1. And if we come across operators such as this plus m, and its usage in the expression is like this, then it means the same as a plus b mod m. Similarly, if we come across an operator like this, and it's used in the expression as, then is the same as a times b mod m. Now, if we are given, let's say we take this example into consideration, we are 7 which is like this, 7 plus 11 and then 9 is the same as 7 plus 9 mod 11, which is equal to 16 mod 11. So the point worth noting here is that it's not congruence, it's just it's just you are equating it. So instead of the congruent symbol, we have equal to symbol here. Then if we have something of this sorts here, this will mean 7 times 9 mod 11. So this will be equal to 63 mod 11. So in this case, what we'll have is this is actually 11 times 1 is 11. So we'll have 5 as the remainder. So this will be 5. And in this case, what we'll have is 63 is divided by 11. 5 times 11 times 5 is 55. We'll have 8 as a remainder. So this will be 8. So you might come across these expressions, and just to make sure what all these symbols mean. So these examples were to impart that idea what all of those expressions mean. And I think I will stop here. If anyone of you has any questions, please go ahead.